All right, here we're looking at section 4 in chapter 3. And our learning targets for today, we're going to be building quadratic models from verbal descriptions and then building those quadratic models from data. And whenever you see this calculator thing, that's where we're going to be, I'm going to be showing you how to use Desmos because that's something you will always have when you have internet access. Okay, so first we're going to start with some verbal descriptions. So the marketing department at TI has found that when certain calculators are sold at a price P dollars per unit, the number X of calculators sold is given by this demand equation. Okay, so first we have to find a model that expresses the revenue as a function of that price. Then figure out what the domain is. Tell me what we're using to maximize. Generally when we're building these models, we're looking for maximizing or minimizing. And that's always finding the vertex of my quadratic function. Okay, so we need to figure out what price I use to maximize, and then if that price is charged, what do I actually get in my revenue, and then how many units are sold. We're going to graph it, and then we're going to look at kind of a system of equations here. Okay, so this is a lot of info. We're just going to start at the top. We know that the revenue is my X times P. So we figured out before that my X equals 21,000 minus 150P. That was the price, the demand equation that we were given. So I know I have to multiply that times P, so I end up with my model, my quadratic, because I have an exponent of 2. Okay, so X represents the number of calculators sold. I know that X has to be greater than or equal to 0, because I can't sell negative calculators. So now I can go ahead and take my original equation, my X equals, and set that greater than or equal to 0. So when I solve that, I see that P is less than or equal to 140. So that's going to be the domain. It has to be greater than 0, but less than 140. Okay, so here's also written kind of in that same way. So my function's quadratic, which we've talked, which I have an A value of negative 150, I have a B value of 21,000, and my C equals 0. Since I don't have any constant over here, my C can equal 0. So since I'm trying to maximize, I want to find the vertex. So to do that, I use my negative b over 2a, and this is always how I find my vertex. This is always the x value of the vertex. So we always kind of start here. So I plug in what I know. So I have my negative b over 2a, which ends up being $70. Okay, so that just tells me what the price is that I need to charge to get the maximum. Now we have to figure out what the actual maximum revenue is. So I plug this 70 back into my original equation wherever I see an X, and I solve. And this gives me my actual maximum revenue. So keep an eye on that, because sometimes the question asks, what is the maximum revenue? You can't just stop here because that's not my revenue. You have to go here because this is how we find revenue. So in part E, we were asked, well, if this price is $70, how many calculators are sold? So that's where I go back to my original just calculator equation. So my X equals 21,000 minus 150X. Well, I plug in my X because I figured out that that needed to be $70, and I see that we sell 10,500 calculators if we sell them for the price of $70. Okay, so then I was asked to graph this, and then what price should I charge to collect at least this much in revenue, right? So there's going to be a couple of places to look. So now first let's graph it. And this is what we end up with when we graph it. And we see that once we've graphed it, we also can find the maximum, which told me at $70 I would make $735,000 in revenue. Okay, so there's my graph. You can also use Desmos, but this is kind of what Excel would look like, or your graphing calculator. And then I'm finally asked, whoops. So I need to collect at least $675,000. So there's several ways I can do that. The first is I can graph this, right? So I can graph my original equation, and I can graph my R, or my Y equals $675,000, because I know I need to get at least that. So you'll see this is this line right here. So anywhere that I cross here, so my intercepts would be 50 and 90. So you see anywhere between these two prices, I make at least that much revenue. And that's what that question asked me. So I need to charge between $50 and $90 per calculator in order to make at least the $675,000. We can also do this mathematically. Okay, so we first graphed it, and then we can also just solve it and simplify. Right, so I set this, my original equation, equal to my 675,000. I get everything over to one side. Then I see that I can divide everything by this 150 to kind of simplify my numbers a little bit. Then I factor. I could also use the quadratic formula to get these two answers. And you see that these two answers give us the same x values that we found from our graph. So that's all we're doing. We're finding it graphically and then also algebraically. Okay. So here's our second example. So we often want to maximize the area that's enclosed by a fence. You'll see this a lot when we're dealing with quadratics. Okay. So the problem says a farmer has 1,600 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that encloses the most area? So we always want to start by kind of drawing our picture and see that I've got the widths and the lengths. So I know that to find the perimeter, which is what the fence is, I have to have my 2x plus 2w equals 1,600. That's just how I find the perimeter of a rectangle, right? I add up all the sides together. So then I know that I'm trying to find the biggest area. So I know my area formula is my length times width, or in my previous drawing, my x times w. So I want to get this all into one variable so I can simplify and solve for that. So I have two different equations I can use. So I'm looking at my first equation, this 2x plus 2w equals 1,600. So I want to solve for my w here. So I subtract my 2x from both sides, and then I divide everything by 2. So when I divide both sides by 2, I can divide each term on the right side. So I end up with w equals 800 minus x. Well, now that I have that, I substitute that into my area formula where I have this w. So now I have x times the quantity 800 minus x, and when I distribute this, I end up with a negative x squared plus 800x. So this is my quadratic function. Okay, so now that I have my quadratic and it's written in standard form, so my highest exponent is first, I have a c value of 0. So now that I have this, I can go ahead and either graph it, and I can also find the maximum mathematically. So first I graph it, right, just using Desmos, and I see that I'm going to limit my domain because I cannot have negative area and I cannot have negative fence length, right? So I can limit my domain, and I see based on my graph that if I have an x value, and x was one of the sides of my field, of 400, I will maximize the area, and this is the largest area that I will be able to get from that perimeter. Okay, so we can also find this mathematically by always using this negative b over 2a. This is kind of our big mondo thing here. Okay, so I plug in the values that I have, and again I come up with this x value is 400. So again, that tells me when the side length is 400, I will have the maximum area. We were never asked what the maximum area was, so we could actually stop here for this problem. Okay, so here's our next example. So we're going to often analyze the motion of a projectile, because if I throw something or hit a ball, any of those things, it looks like the shape of a quadratic. Okay, so here I have a projectile that's fired from a cliff 500 feet above the water at an inclination of 45 degrees to the horizontal with a muzzle velocity of 400 feet per second. From physics, here's my equation that measures the height based on the time after I've based on the distance of the projectile from the base of the cliff. So just keep in mind when we're looking at these word problems, we always want to keep in mind what our variables are, because here it's distance and not time. So first I have to find the maximum height, and then how far from the base will the projectile strike the water. So first we always kind of draw ourselves a picture just so that we know what we're looking at, right? And it starts at 500 feet at an angle of 45, it kind of goes up, and then it crash lands. So based on my graph, I see that it's about 2,500, but I want to make sure. So we're going to do it mathematically too. So the maximum height is going to be our maximum value here. So again, I use my negative b over 2a. So I substitute in the values that I have for those, and I see that it was 2,500. So 2,500 feet after I release it, or after I shoot this, it will be at its maximum height. So now I can find the maximum height by plugging this value back in whenever I saw an x, and coming up with that maximum height will be 1,750 feet. So first I have to figure out how far away that will happen, and then I can figure out the height. Then I was also asked, when's it going to hit the water again? So I have to figure out when my height is 0. So I set my entire equation equal to 0, and I know that I'm going to have two solutions here. So I would use the quadratic formula, because these are not going to be easy numbers to factor. So I use my quadratic formula, and I plug in my A, B, and C's, and I come up with these two solutions. We know we're not going to use this negative solution because I cannot have a negative distance. So we're only looking at this distance. So the projectile, or the cannonball, whatever it was, will hit the water 5,458 feet after we shoot it. So from the base of the cliff. So our next example, we're looking at the Golden Gate Bridge. Okay, so here's our suspension bridge that spans the entrance to San Francisco Bay. The towers are 746 feet tall, and they're 4,200 feet apart. So again, we're going to drawing our picture as we go. So it's 220 feet above the water. So that's where we get this 526 from, and that's going to be a very important number. We also know that this is 2,100 feet because the entire thing is 4,200 feet. Okay. We always generally, when we're dealing with these word problems, we want to set our vertex at the origin. Just makes it a little bit easier to deal with. Okay. So now I know that I have a point, this negative 2,100 and then 526, and then a positive 2,100, 526. So I know that those two are on my graph, which allows me to kind of solve for things. So now I know I have ax squared because I don't have, my vertex has not moved. That's why we always want the vertex to be at the origin. So I just substitute in, I pick one of my points, and I generally pick the one with positives. So I plug in my a and my x and my y, and I simplify and I solve for that a value. So here's what that a value is. So now I can write the actual equation. So here's the equation that models the Golden Gate Bridge. And then I was asked, well, when I'm 1,000 feet from the center, how high is the cable? Well, so now I can actually put that into my equation. So when I'm 1,000 feet away, I plug that in, and I see that the cable is at approximately 119.3 feet. So now we're going to be looking at data, and this is really where we're going to be using Desmos. Okay, so again, we're just going to look at our trends. So here I would definitely say that we're going to have a minimum value, and here we're going to have a maximum value. And we can look at the A values based on that as well. Okay, so we're going to look at some data, represents the percentage of the population that is divorced. So first we have to draw our scatter diagram. Then we want to find the line of best fit. And it's not going to be a line of best fit here, it's our quadratic function of best fit. And you can use your graphing calculator. I've gone ahead and used Desmos since that's what we'll use most often. Then we're going to use this data and this model to predict a couple of things. Okay? So here's the data population. And what I've gone ahead and done is I've put that into my table in Desmos. So here you'll see the data that we used. So then, using Desmos, I can also use my quadratic regression. All right, and we've done this with linear regression. It's the same sort of thing. So this is the equation I'm going to type into Desmos. So this y1, and I have to specify 1 because this is in table 1. So y1 is approximate that squiggle that's above your tab key, ax1 squared plus bx1 plus c. So I see that a quadratic fits this data pretty well because this is almost 1. And here's my a, b, and c values that I can plug back in. So I was also asked to find the percentage where it's the greatest. So again, I can use Desmos and I see that, well, at the approximate age of 55, the percentage is the greatest because that's just the maximum point of my graph. Okay, so we looked at our scatter plot. We used our regression. It just looks a little different in Desmos and came up with our model. Okay, so we found the maximum. We can also do that mathematically. We clicked on the maximum point on the graph, but I can also use my negative b over 2a and plug in the values from my equation to find the age when there's the maximum divorce. Okay, so now part D asked us, okay, so what is the percentage at that rate? So now I can plug this in anywhere I see an x in my equation and get to 15.8%. You'll see that it's also here in my Desmos when I use that. So both will get me the same solution. Okay, so then we just had to draw that scatter plot again. Okay, so now we've actually worked through all of the learning targets. So let's just double check. First, we built quadratic models from verbal descriptions, and then we looked at data. And when we look at data, we can't just use the points. We have to use a graphing utility because we need to find the most accurate fit. So now that we've worked on these learning targets, go ahead and work on your homework for this section.